If you look at the periodic table, you'll see each one, there's 118 elements. Each one has their own particular symbol. On top of the symbol, which represents that particular element, there is a number. That is the atomic number. Each one, there's 118 numbers, each one specific for that element. Underneath the letter is a decimal number. For example, if you look at number 4, beryllium, it has a number listed as 9.01. And that is what we call the atomic weight. And what I was stating earlier is that when you will eventually use that number in your calculations, that to use the periodic table that we supply. Because if you look it up someplace else, you will be given a little bit different numbers or even more digits. And I'll explain more about those digits further down the road. And when you do the calculations, your answer would be a little bit different than what Canvas accepts and count it wrong. Though it's not wrong, and I will give you credit for it if your number is within, a couple of decimal places. But if you use the atomic weights here, then we shouldn't have a problem, okay? So 118 different elements, each one a unique name. Now, the first letter is always capitalized, so you won't find any lowercase first letter for the symbol of the element. If there is a second letter, which you saw there in the product table, yes, that one is lowercase. And that's important too, because you don't want to mistake, for example, CO. If CO, capital O, was written thinking that is cobalt, which is C lowercase o, totally different species. CO, both capitalized, is carbon monoxide, okay? Whereas C lowercase o is the element cobalt, totally different components, species. All right, most of them have English names, H for hydrogen, oxygen, helium, so on and so forth, okay? There are some that are derived from Latin names. For example, PB, which is lead, comes from plumbum, which means waterworks. Okay, lead was used quite a bit for sealing tubes or plumbing plumbing drains. And AU, Orium, which means golden dawn. Okay, so be familiar with the first 20 elements. In other words, be familiar with their names and their symbols. Okay, so that would bring you up to 20 would be calcium. Okay, so starting from hydrogen, you can go across a little bit. So if we start with the far number 1, we got hydrogen, and then it shoots across the table to the far right to helium, number 2. Okay. Then let me do this so we can make sure we're in the same spot. So we start with hydrogen here, and then we shoot across to He, which is helium. And then we got number 3, which brings us back to the beginning of the table on the far left. We got Li, which is lithium. Be is beryllium. And then we shoot across to for number 5, which is B for boron. C for carbon. N for nitrogen. O for oxygen. F for fluorine. And E for neon. And then we go back to the left, far left. We get Na, which is sodium, and G, which is a magnesium. And then we go Al across to this particular group. I'll mention these Roman numerals up on top. They're very important. Aluminum. And then for number 13, number 14 is silicon. Number 15 is P for phosphorus. And then S for sulfur. Cl for chlorine, and then Ar for argon gas. And then we go to 19 K for potassium, and then finally 20 Ca for calcium. Okay, now these are the elements. Okay, and being elements, they have zero charge, and this may be clearer more so than later on as we talk more about it, because obviously you know that calcium is important for your body, but you're not eating calcium ion, calcium elemental calcium. You're eating the calcium ion, which has lost some electrons. The same is true with sodium. You're not putting sodium metal on your French fries. You are putting sodium ion that has lost an electron. Okay, and it'll become clearer as we progress, but we can use the periodic table to give us a heck of a lot more information. So that's why we refer to the periodic table. I refer to it quite a bit. So be aware be familiar with the first 20 elements. And then on top of that, learn these metals, and there'll be more coming. Not a lot. We're not gonna sit there and have you memorize all 118 elements, but definitely give you the ones that are used quite often. And so at least the first 20, and then on top of that, Ag for silver, Au for gold, Pb for lead, Br for bromine, I for iodine, and Hg for mercury. Okay. Now, when we talk about the physical states of the elements, again, we're talking about 25 degrees Celsius, which is basically room temperature, and 1 atmospheric pressure, and that is approximately where we're at now, 1 atmosphere. Okay. So of the 118 elements, only 2 elements are liquid, and that is mercury and bromine, and that is at 25 degrees Celsius. Obviously, if we're on the surface of the moon, everybody would be gases, right? But we're not. So at 25 degrees here on Earth, mercury and bromine are the only elements. Now we have hydrogen and 2. Remember, these are diatomic. I talked about that as subscript. Diatomic elements: hydrogen, nitrogen, oxygen, fluorine, and chlorine. So that's 1, 2, 3, 4, 5 of these diatomic elements, plus what is called noble gases. So what does that mean? Notice I say group Roman numeral VIIA. That's group 8A. So let's go back to the periodic table. And that would be these right here, the far right. Okay, these are what we call noble gases. And we call them noble gases because they are very unreactive. And hence they give it the term noble, meaning they're not going to react. Another one like that is gold. Gold is a noble metal because it's very unreactive. And so we got 1, 2, 3, 4, 5, 6, 7 noble gases, plus the 5 we showed earlier. So that's 12 elements that are gases at 25 degrees Celsius. Okay, and bromine, which is right here, and mercury, which is right here, are liquids. Okay, and so we have 12 gases, 2 liquids, and guess what? Everyone else is solid. Okay, solid. So this periodic table shows you at a glance, you can determine whether one of the elements is a solid or liquid. As stated earlier, the bromine and the mercury, which are kind of in color, I guess, light purple, are the only liquids. And then all the ones in yellow are gases, okay? And so at a glance, once you be able to say, oh, okay, this material at 25 degrees, this element is a solid or it's a liquid, okay? Now, remember I stated earlier, there are 7 elements that are diatomic. At 25 degrees, they function as, they're not stable. So they need another one to be with it to be stable. And that's hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine, going from left to right. And we have something here to help you out. It says, have no fear of ice cold beer or have no fear of ice cold beverage, whatever suits you best, okay? And that kind of helps you out to determine which ones are diatomic, which is important to know because you may be given a sentence of a reaction, like earlier said, sodium metal reacts with chlorine gas to give you sodium chloride. So we have to know that chlorine is diatomic, okay? Now, because we're going to come and we have to balance this equation. I didn't talk about those coefficients that were in front. These are subscripts, and numbers and obviously are subscripts to tell you how many atoms they are. Once the subscripts are set, we don't change them, but we can put a number in front of the molecule and we can change that number as much as we want. So I can put a 3 in front of chlorine, tells me I got 3 molecules of chlorine, or I can put a 5 in front of bromine, or I can just put a 2, whatever it takes. I can change this coefficient as much as I want. The subscripts are etched in stone. Those we don't change because that's how the molecule is put together to make that particular compound, whatever it may be, whether it's a molecule or a compound, okay? So we don't change the subscript, but we can change that number in front of it all we want, which is called a coefficient. All right, now with respect to all the elements, 118 elements, they're only classified as 3 types. We have what are called metals, okay? Then we have what are called nonmetals, and then we have something that's called a semi-metal, AKA metalloid. Well, some people have a challenge with a semi-metal. Well, think of it as a mule. I don't know if you know how a mule comes about. Does anybody know what a mule's made up from? Anybody know? Let's see. We got a chat here. Exactly. Okay. A horse and a donkey, both Mason and Tyler. And so having properties of a donkey and probably properties of a horse, you end up with a mule. Okay. Well, semi-metals are the same way. They are in between. They have properties of metals and they have properties of non-metals. Okay. Now, we're not going to work a lot with semi-metals. We're going to be the majority, 99% of our work here in school, in Chem 130 will deal with metals and non-metals. Okay. Now, the thing to remember, I'm going to introduce this early, but put this in long-term memory. Okay. When we talk about subatomic particles, and I said earlier, all the actions happen with the electrons. The electrons are the ones that the chemical reactions are that's what happens. You're going to lose or gain electrons in these chemical reactions. And that being the case, all metals gain, what am I saying? Lose electrons. can't write it very well. Lose electrons. Sorry about that. I was thinking of something else. Okay. Non-metals, put this in long-term memory. Gain electrons. Okay. That's important because we have to first identify if it's a metal. If we identify if it's a metal, then what do we know? We know that it's going to lose electrons. If it loses electrons, guess what? It's going to end up with a positive charge. Why? Because electrons are negative. And you lose negativity, you become positive. Okay? So remember that. The other thing is non-metals. Since they gain electrons, which are negative charge, guess what charge they're going to end up with? A negative charge. And that's important too. Okay? Because by gaining electrons, they have a negative. And that is what you, and these guys, by losing and gaining electrons, this is what makes up ions. You may know them as electrolytes when you're taking your electrolyte drink, you know, because you've been working out and you want to replenish your electrolytes. Electrolytes are nothing more than ions, which are nothing more than elements that have either gained or lost electrons. And so if you're low on iron, you're not chewing on a piece of iron and chewing that down. No, you're not. You are actually taking an ion supplement, which is an ion, because your body will use that. Your body uses ions. It doesn't use the element itself other than oxygen. And that's a whole different story there. Okay. All right, let me clean this up. So non-metals are located to the right of the stair-step line. Now, what are we talking about stair-step line? If you have your periodic table out, okay, you see here that stair-step. The metalloids are on the stair-step, okay, on the stair-step. And actually, the way that works is this. You can do it this way. So we start with boron, we go to silicon. Then we go down to uranium and then across to AS, okay? And then down this direction and then across this way, down this way, and then across, and then down, okay? And across. I got to double check on 118. I believe 118 is classified as a non-metal. But basically diagonal, then down, across, down, across, down, across. So on that stair step are all the metalloids. So that means that everything to the right of that stair step are non-metals. Everything to the left of the stair step is a metal, with the exception of hydrogen. Hydrogen is a non-metal. Okay, even though it's on the left of the stair step, it's placed there in that position for a particular reason. But it's a non-metal. Don't forget about hydrogen. Okay, don't think of it as being a metal. All right, so let's go back. And so here's the semi-metals, and then the metals, and this is the particular, the colored, the periodic table color coded to tell you the pink is the non-metals, the blue are the metals, and the yellow are the semi-metals. Okay. So 118 is no, it's not a metal, is not a metalloid, but I'm fairly 100% sure. Number 17. Notice that 117, 118, and 115, they have letters. Those were temporary letters because those elements at the time of this periodic table had not been created. They have been created about 2-3 years ago, and they had just recently been given official names, and they're still studying the properties of them. So that filled up the periodic table. And now scientists are working on 100. Oh, okay. Thank you, Skyler. That's the name of it. They gave them some interesting names. um, oh, what was I? So they're working on others, and when 119 comes about, guess what? It's going to be right underneath 87. Okay, that is where it's predicted to be. Now we're going to learn a lot more about the periodic table, and because the periodic table we think about has some periodicity. There are some trends we can look at the elements and just knowing by its position on the periodic table, we can know all kinds. You're already beginning to know this. If I were to say to you, number 20, calcium, is it a metal or non-metal? Well, now you know that it is a metal. Okay, based on what I just told you about metals and putting a long-term memory, the question would be, would it gain or lose electrons? And now you can say it will lose electrons because it is a metal. Okay, now the next question would say, well, if it loses electrons, how many electrons would it lose? Now you can answer that question because knowing that it is in group Roman numeral 2A, and I'll explain more in detail what that means. But for right now, calcium will lose 2 electrons. Okay. In fact, everybody in this same group will lose 2 electrons. What does that tell you about the group 1A? Everybody here will lose 1 electron. Okay. And all the metals in group 3A will lose 3 electrons. The metalloids depends on the conditions. We can't predict that. Now, the pink, which are the nonmetals, will gain electrons. Okay, so everybody in pink there, including hydrogen. Now, hydrogen is very unique because it's in that group 1A. It can lose 1 electron, but you're going to learn it can also gain an electron, but more on that later. But for right now, let's look at the nonmetals. The thing to remember is that everybody wants to be like the noble gases that I showed you, group 8A. Everybody is striving to maintain a magical number, 8 valence electrons. Valence meaning that every one of these guys has a different number of electrons, and valence is the outermost shell. All these electrons are going to be in different energy levels we're going to learn, okay? And the drive of all chemical reactions is to get that magical 8, where we have 8 electrons around the outermost shell or the valence shell. It's going to occur by either losing electrons or gaining electrons. And if we look at all the nonmetals in group 7A, okay, guess what? Since they're nonmetals and they're striving for the magical 8, and they're in group 7A, Roman numeral 7A, how many electrons do you think they need? What can you conclude based on what I just told you? They're in group 7A, that's Roman numeral VI, okay? They're striving for the magical 8 number. So, and they're non-metals. So how many electrons do you think those guys that I just highlighted here, those elements, need to get that magical 8? They have 7. What do they need? Exactly. They need 1. So everybody that's a non-metal in group 7 will gain 1 electron. Okay. Let's take it one step further. How about the next group in group 6? How many electrons? They're all the non-metals. How many electrons do you think they're going to gain? They're in group 6. Exactly, Skylar. Name me 2. See, you're already learning here. How about group 5? Give it a shot for the non-metals. How many electrons do you think they're going to gain? 3. Exactly. Now, Here's next one, carbon. You might want to say, okay, it's in group 4. What do I do now? Well, guess what? Being in group 4, think of it as it being on the fence. Okay, you're on the fence. You're gonna fall to your left or you're gonna fall to the right. Now, carbon and everybody in group 4 will either gain 4 because they're striving for the magical 8, or guess what? They can lose 4, and it all depends on the reaction conditions. So in the special case here, group 4, lose or gain 4. So anybody in group 5 forward will gain whatever number they need, and anybody in group less than group 4 will lose. Okay, and when that happens, remember the electrons have a negative charge, and if you gain an electron, you're going to end up with it. Like group 7, you gain 1 electron. Everybody in that group is going to have a negative charge. So you end up with a negative charge, -1 charge here for everybody there. Group 6 will end up with a -2 charge, and group 8 will end up with a -3 charge. Those are what we call the ions. Okay, everybody here will have a +1 charge. Everybody here will have a +2 charge. Now, we can't do that to all the other metals in here. What's happening is that these guys that I just circled, it depends on the reaction conditions. The only one we can do this prediction for are the elements that are in the A group, okay? And we put them all in the A group because they all have similar reactivity. And the reason they have similar activity is because they have the same number of outermost electrons. And so lithium, even though it has 3 electrons compared to potassium, which has 19 electrons, what they share in commonality is 1 electron is in the outermost shell. And that's why they react so similar. Okay, the same is true for the other groups. Now, let me give you another trend that you can deduce and some information. Now, we don't have it here, but the periodic table I have, you can number these, put 1, 2, 3, 4, 5, 6, and 7. Okay, and that represents what we call the energy levels. We have 2 elements in the first energy level, and that's hydrogen and helium. And then second energy level, third, fourth. There's only 7, okay? And think of those as layers of an onion. We got a small onion, we got another layer, we go up to 7. And so with that in mind, can you predict, let me clear this up a little bit. Who do you think would be bigger in diameter? Lithium or potassium? Who do you think is bigger? Just based on what I just told you. Exactly, potassium. Potassium. Because potassium is in the 4th energy level. Okay. I'm running out of space here. So 1, 2, 3, 4, 5, 6, and 7. So potassium's in the 4th energy level, whereas lithium is in the 2nd energy level. So it's like in the potassium is a bigger onion. Okay, it's a bigger onion than lithium. So going down the periodic table, guess what? The elements get bigger. Okay, and we're going to learn some more trends about that as we go across. But for right now, I don't want to jump too far ahead. Right, so this table tells you who's the metal, who's the non-metal. Now you know about electrons and what charge they're going to have. We're going to learn later on why, but hopefully it makes more sense here for you. And But you already picked up on some trends, really, by just going down the periodic table. The radius gets bigger. Now you know which ones are the metals and which ones are non-metals. So that also tells you, oh, when they become ions, now I know which ones have a positive charge and which one will have a negative charge. Okay. Some of the properties of metals versus non-metals. Metals tend to have shiny appearance. You can smack them and spread them out and really pull them and stretch them out to very small size. Back when I was working in industry, I used to work, as I stated, with copper metal. I had an opportunity to see the operation of how they make these copper metals. In our source was in Finland, and they would start with a block of copper metal, a particular alloy, roughly about 4 feet thick, and maybe about, I don't know, 8 feet wide. So it was pretty big. And they would take that thing and roll it back and forth in this gigantic mill. And they'd take that big 4 foot thick piece of chunk of metal and bring it down to about 1/4 inch size. So that's one of the properties of metals, that you can smash them. They're ductile and malleable. So all metals are solids with the exception of mercury. Mercury is not used much as it used to be. Now with the more electronic thermostats, they used to be used quite a bit as thermostats, but not so much now, because mercury is not a good metal. It's a heavy metal, can cause problems health-wise. Generally have a high density, okay, and their melting points are pretty high. That implies that the intermolecular forces that hold the atoms together are pretty strong, because it takes a lot of energy to break them apart and shove them into the vapor phase. All of them are good conductors. Metals are in general very good conductors of electricity because of the amount of electrons they have. And being a good conductor is a general rule of thumb. They're also good conductors of heat. Okay. With respect to nonmetals, those that are solids have a dull appearance. If they're solids, they tend to be very brittle in nature. And a lot of them are metal gases. Okay. Density generally kind of low compared to metals, and a very low melting point, again, compared to metals. And they tend to be poor conductors of electricity. Not that they can't conduct, they're poor conductors. They can conduct, but they're not very good. And they're better insulators, if you will. All right. So, all right, with that, that information, take it when you look at our periodic table, the one we supply, be able to determine the name of at least the first 20 and the ones we gave you. Okay. Determine whether they are solid, liquid, or gas. Look at slide number 2035. Okay. Determine whether it is a metal or a non-metal or semi-metal based on their position. So it's not necessary. I don't advocate memorizing the properties of each one of those, but just be familiar with the periodic table and the ones we give you here, the trends. So pick out whatever works for you. And then if you know where all the gases are, then you know where all the non-gases are, right? So that being said, and there's only 7 diatomic. Okay, whether it's a diatomic, we know how many are gases, we know how many are liquids. That can tell you how many are, which remains is the number of solids, and which ones are diatomic. Have no fear of ice cold beverage to help you out. Okay. Whoa, crazy. All right. Congratulations, you're done with chapter 1. Which brings me to chapter 2. Before I begin, you have any questions? No? Okay. All right. Here we're gonna talk about the math, okay, involved with respect to calculations and how to convert from units. Now, the technique that we utilize is important because that really we're going to use the same technique to do our calculations with chemical reactions. Okay. And so, I know, and I say this every semester, I know a lot of times people have been taught to use the ratio system to do conversions from one to the other. I don't recommend using that technique in these type of calculations because when we get to chemical reactions, what can happen, we can have 3 or 4 conversions. And if you're using the ratio system, that's where you've been taught, that can really send you off the left field and you're totally completely out of where you've been. And so what I advocate is using this technique where we're basically keeping track of units and we're making sure that units cancel out. And if I set those up properly, I can guarantee you 99% of the time you've got it set up properly and you just a matter now plugging the numbers into the calculator and you're good to go. Okay, so let's talk about measurements. Okay, obviously a measurement is simply a number, but more importantly than that, it is a number with some type of unit. Okay, now we're going to be using metric units, grams, kilograms, whatever, but be metric units. Now we will do conversions from English to metric simply to demonstrate this technique that we utilize to get from point A to point B. Okay. Now, a number is important, obviously, but more important than that, we need a unit. So if we got something that says the book weighs 8, what does that mean? It doesn't mean anything. We could have said 8 pounds, 8 tons, 8 ounces. That's the problem because does not have any units. Okay. The other thing that we need to grasp with respect to units and numbers, that all measurements, anything that you measure has a degree of uncertainty. Okay. And a lot of times you have to estimate that last digit. And because there's a degree of uncertainty, we have to deal with what is called significant figures. Okay. Now, let me restate that. All measurements, keyword measurements. So if you measure the mass, we measure the length, we measure the volume, which is basically the 3 measurements we'll be doing. There's always going to be a degree of uncertainty. That last number, I look at it, maybe I'm measuring the volume. I might see it as 12.2 millimeters, for example. You look at it, you might see 12.1. My number is not wrong, nor is yours. Okay. Because that last digit, that point, whatever, is that degree of uncertainty. And so we have to deal with significant figures, and we'll have more on that in a second. With respect to length, the kind of units that we utilize are centimeters, millimeters, meters, and kilometers or kilometers. Okay. Measurements, some rulers have more marks than others, right? If we look at the white ruler, we can see that is least accurate because there's less marks there to give us a more accurate reading. If we were to try to, let's say we had a measurement that we were looking at, right there, you can see that we're going to have to estimate with the white ruler, but with the brown ruler, we can be a little bit more accurate. Okay. Now here's what's important. If these 2 measurements, if we did a measurement with the white ruler, and if we did a measurement with the dark ruler, the brown ruler, and we needed those 2 measurements to, let's say, calculate the area, length times width, well, our answer could not be more accurate, than the accuracy of the measurement from the white ruler. Okay, that is what we talk about when we talk about a degree of uncertainty and significant figures. I realize that when you plug in the numbers in the calculator, you can end up 10,000 digits, and you really would be incorrect to state all those 10,000. I'm exaggerating, 10,000 digits, right? Because you weren't that accurate. Okay, you weren't that accurate in your measurement, and so we could not have more accuracy than the least accurate measurement that we have. That's the thing to remember here when we talk about significant figures. Okay, cannot be more accurate than the least accurate measurement. Okay, so obviously here, which ruler has more uncertainty is the white one. Yeah, because we're really estimating mass. Okay, the units normally used in mass are mg for milligrams, kilograms, or grams. Okay, we have two types of balance here. We got the balance in the left, which is called the triple beam balance. And normally what you do, you put weights on one side, and then you got your whatever you're going to measure in the right side. And then you got the one on the right, which is probably the type of balance we would actually use in the lab, is a digital balance. And those accuracy, we can go to like 3 decimal places with the electronic balance. A lot more accurate with respect compared to the one on the left. So again, the one on the right would be more accurate. And if we were going to take measurements and weights, mass, and use them in calculations, we couldn't use, we could not report a number more accurate than the least accurate measurement that we have here, okay? Mass versus weight. Now, we tend to interchange this term, okay, simply because we're stuck here on Earth. But I think we all know that mass and weight are a little bit different. Weight is governed by the gravity on your planet, which is this one. Okay, compared to the gravity on the Earth, my weight would be different on the moon, I should say, than the Earth. Okay, but my mass, which is a measure of all the matter I have in my body, since the corona, I picked up a little bit more mass than normal. Okay, so my weight is changed here on Earth, but if I went to the moon, I would have lost weight only by measurement, not by mass. Okay. By definition, weight is equal to the mass times the gravity here on Earth, which is, I believe, 9.8. Is a gravity factor, 9.8 something meters per second square, I believe. Anyway, so that gravity would change depending on where you're at. So if you weigh 170 pounds on Earth, you're going to be about 29 pounds on the moon. Okay. So, but we interchange that. Okay. So you might hear me say weight, which I'm talking about mass, and vice versa. Volume, our units normally are liters, capital L, or we could use KL, kiloliters, or ML. Most common one is ML and L for liters. These are types of equipment that is used to measure volume, different types that if we were in the lab, we would be utilizing, but we're not. Now, syringes, we're familiar with this. What type, anybody know the type of units syringes generally have? You know, you gotta get a shot. What do you got? Oh, yeah, you got a lot of answers here. Yeah, CC, exactly. Anybody know what CC stands for? Yeah. Okay, cubic centimeter, exactly. CC is cubic centimeters. And so now when you're given a CC, and those are metric units, okay, it's a measurement length, width, and height, all right? But we can convert that to milliliters because the conversion factor is 1 milliliter is equal to 1 cubic centimeter or 1 cc. Now, here's the thing about this conversion factor. Every conversion factor you have, for that matter, every ratio that we're working with can be written in one of two ways, okay? I want you to remember this. Every conversion factor, every ratio, miles per hour, dollars per hour, millimeters per cubic centimeter, okay? This conversion factor can be written in one or two ways. And I could write 1 milliliter over 1 cc. Oh, that's a cc, sorry. Or I can write it as 1 cc over 1 milliliter. Okay. Now, which unit I use depends on the question that I've been asked. And so if I need to convert cc's to units, the question says, all right, I have 100 cc's. Okay. How many milliliters is that? Okay, would be the question. Well, I know that's my conversion factor. And since I'm looking for milliliters, guess what? I need milliliters in this one on the left. I need milliliters in the numerator. Why? Because I'm going to multiply this factor by, keep writing centimeters, okay? Because my units will cancel. My units of cc will cancel, leaving me with units of milliliters. Now, if I were to set it up like this and the other way, 100 cc's over here times this factor, well, my cc's don't cancel. So this would be incorrect in this manner. And this is what I mean by setting up your conversion factors with the correct units and keeping track and following your units. Eventually, we're going to be at a position where we're going to be using in our conversion factors at least 3 back-to-back conversion factors. And by keeping track of my units all along and making sure things cancel out, I got it to the right units that I'm looking for. Okay. Now, let me clear this up. I will give you an extreme example of this to demonstrate this conversion factor. Anyway, I got this image here to help you out for the English units. I always had trouble with that. If you notice this crazy looking image here, you got the big G there, okay? Now, within the big G, guess what? You have 4 Q's, which represent 4 quarts, okay? Now, within the quart, you have 2 P's, which represents pints. So there are 4 quarts in a gallon. The G is the gallon, Q is a quart, 4 quarts in a gallon. There are 2 P's or 2 pints in a quart. And then within the pint, there are 2 cups per pint. And so you have, in effect, using this little image here, to have your conversion factors, where you have 2 cups is equal to 1 pint, okay? 2 pints is equal to 1 quart, and 4 quarts is equal to 1 gallon. These 3 conversion factors can be written either 2 ways. The first one, 2 cups and 1 pint, could be written with cups in the numerator or cups in the denominator, okay? The same with the pints and the quarts and vice versa. So I got a total of 6 ways to write these conversion factors, of which I can set up as I need to go from point A to point B. Okay. All right. Obviously, reading volumes, might be given questions about this. Now, whenever you put a liquid, mostly an aqueous liquid, there are some liquids that do the opposite, but most liquids, when you put them in a cylinder, they form this convex curve. Okay, we call that the meniscus. And the way we read this volume is we read the bottom of the meniscus. And so we're reading right there, that layer right there. Put an arrow on it. Okay, that's the bottom meniscus, and that will represent the volume of this particular. Now, the thing to note about reading your volume do make sure where your 0 point is. If you look at this, this is called a graduated cylinder. If you look at the bottom of it, that's a 0 point. So you're reading this direction, okay? So it's 20 and whatever the number is. And sometimes students start from the top and read it from that direction. That will be incorrect, okay? So do know, but there are some containers that start the 0 on the top, and then that will be correct on the right side. So just make note of where your 0 point is, okay? And so, yeah, about 21 and a half, okay? You know, I could say 21.6. Others could say 21.4, yeah? And it varies. That last number is the uncertainty. Everything has uncertainty, and it's always the last number. The 21.5, the 21.4, or the 21.6 would not be an incorrect number, okay? Because, you know, it depends on where you put your head too, because when you're reading the meniscus, if you don't have it straight on, you're going to read it incorrectly or maybe slightly different. All right, so keep that in mind. If, for example, if you have a problem like this and you answer it and you're 100% sure you're correct, shoot me an email. I'll look at it. I'll definitely give you credit for it if you read it one way. But Canvas has a range of correct numbers, so I think we covered the whole possible correct answers. All right, which brings us to what we call significant figures. Now, the point of significant figures is this: it does not mean that the numbers don't count. All the numbers we utilize count. That's important. Doesn't mean that at all. What that means is what I stated earlier, that when we present a value in some type of measurement and we use it in calculations or whatever we do, we just want to present the value of a measurement, we cannot be more accurate than the accuracy of the tool that we have, okay? Also, if we use those measurements to do calculations, multiply, divide, add, subtract, we cannot be more accurate than the least accurate number. And that's what all this chat part is about. We as scientists try to be as accurate as possible, but a lot of times, you know, even though we have equipment that give us all kinds of numbers, we got one measurement that is not as accurate. So we can't be as accurate than the least accurate digit. All right, so significant figures. We have, you know, all the digits are in the measurement are you going to be plus or minus whatever, depends on how many decimal places we read. Okay, and we know that a bathroom scale versus a surgical scale, you know, that the surgical scale is going to be a lot more accurate. Okay, therefore we have more significant digits because of the accuracy, as we did earlier with the ruler here. You can see here. Anybody want to take what kind of number would you get for the top one? Obviously, it's 29 something, right? Yeah, I got 29.2. Yeah, that's reasonable. 21.3 is also reasonable. But look at the bottom down here. Look at the bottom ruler. We can get even more accurate. Okay, what would be using the bottom ruler? What do you guys think we could get? Yeah, 22.2. Notice that the top ruler, we can only get as accurate as to the first decimal place, the 10th place. Whereas the bottom ruler, we can go up to the 100th place, 2 decimal places, right? So yes, we got more accuracy with the bottom ruler. Now, if we were using these two numbers to multiply each other, our answer should not be more accurate than the top ruler, because that is the least accurate measurement. Okay, so even though we would multiply these numbers, we would get all these digits, we could not report all those digits because we're governed by the accuracy of that top ruler, which is the least accurate. Okay, and we'll see that in a bit. Well, we have to learn about significant figures first. And again, keep it in mind, it doesn't mean whether it's good. It doesn't count for the value of it. Yes, they all count. Okay, we're talking about significant figures with respect to the accuracy. Now, all integers count as significant. Therefore, this number of 4895.2 has 5 sig figs. Okay, 5 sig figs. Oh, wrong way. The second one, the leading zeros in the number, in this decimal number, all they do is signify the decimal place where your value begins. Okay. And so for leading zeros in the number do not count as significant. So in this example, 0.0005454 only has 4 sig figs. 4 sig figs. Those leading zeros don't count. Now, when it comes to zeros, I'm going to show you a little trick, a little tool to help you out to see if it counts or not. Okay, but let's go through the book's rules first. I'll simplify it here in a bit. Captive zeros, those are zeros that are between integers. They count. They're counted as being significant. So the number 3050, 3050 would only have 3 sig figs, because that zero in between the 3 and the 5 would count, whereas a 0 by itself does not count as being significant. The number 0.002001, the first 3 zeros are based on rule number 2. Those are leading zeros and therefore don't count. And then the zeros between the 2 and the 1, based on being captive, count. So that number has only 4 sig figs. Now, when it comes to multiplying and dividing, and right now I'm just talking about multiplying and dividing, if I were to multiply 3050 with the bottom number 0.002001, my answer should have no more than 3 sig figs, because 3 sig figs, the 3050, is the least accurate number, as the least number of significant figures. Okay, you see how that is working? For example, if I were to multiply the example in number 1 with the example in number 2, then my answer would only have 4 sig figs. Whether I multiply or divide, and right now I'm just talking about multiplying and dividing, my answer would have no more sig figs than number 2, which is 4 sig figs. Okay, so that's why it's important. We have to figure out how many sig figs it has, so we can determine how many sig figs our answer should have. And then trading zeros. Okay, zeros after decimal point and a number count. So 0.0880 has 3 sig figs. Okay, and 28,500 only has 3 sig figs, which brings me to the point when it comes to 0. The number 4 tells it all right there. If you have a 0 and you're not sure whether it counts as being significant or not, ask yourself 2 questions. Question number 1, is there a integer in front of that 0? Okay. If the answer is no, then it doesn't count. You don't have to go any further. Look at that. Look at the leading zeros in number 2. Those 4 digits, the 4 zeros there is no integer in front of them, so they don't count. You don't have to go any further. Okay. Now, if look at the 0, let me point the arrow here. Let me do it this way so we can see. 0.0880. All right. So looking at these 2 zeros here, there's no integer in front of them, nothing over here, so they don't count, which is consistent with rule number 2. Okay. Now, if we look at the 0 over here, and you ask the first question, is there an integer in front of it? And sure enough, guess what? There's an 8 in front of it, so that's a yes. Then the second question is there a decimal point anywhere in that number? If you answer yes the second time, guess what? It counts. That zero counts. So that number has 3 sig figs. Okay. We know automatically that integers count, so you don't have to ask any questions on that. And the other one is when they are captive between integers, it's automatically they count. Okay. So take a look at these zeros right here, or both of them. Okay. First question. Is there an integer in front of those two zeros? And you say, yes, there is. There's a 5. Okay, good. That's a yes. Second question. Is there an integer anywhere in this number? Answer is no. Therefore, those zeros don't count. There's only 3 sig figs. You see how that works with respect to zeros? Okay. Now, when we get to the actual mathematics, and let's say, for example, if we were multiplying or dividing these two numbers, okay, our answer would have 3 sig figs because both of them have 3 sig figs. They both have 3 sig figures. Our answer would have 3 sig figs. Over here, one has 3 sig figs, one has 4 sig figs. Our answer, if we were to multiply or divide these numbers, would only have 3 sig figs, our answer, okay? And the same would be true here, or not the same, but this, if we were multiplying or dividing these two numbers on top, then our answer should only have 4 sig figs, okay? 4 sig figs, only for multiplying and dividing. Adding and subtracting have a slightly different rule. However, it still deals with finding the least accurate number. It's a little bit different. And I state that because I don't want you to mix the two. When we multiply and divide, we think sig figs. When we add and subtract, we're going to think decimal places. That's it. And we don't mix and match the two separate. Okay. All right. So for example, here, finally 285.88. Again, this has 5 sig figs. Okay. Ask yourself the questions for those two zeros. Is there a decimal integer in front of them? The answer is yes, there's a 5. Okay. Is there a decimal point in that number? Yes. So therefore, those zeros count. Now, the moment I take a number and I insert a decimal, I make the zeros count. For example, if I were to say 285, okay, how many sig figs does 285 have? 3, exactly. The moment I stick a decimal point and I add a 0, guess what? How many now? 4. In fact, the better example would have been 2850. Everybody agreed that 2,850 has 3 sig figs. Okay. The moment I stick a decimal point in there, bam, now I have 5 sig figs. Okay. All right. So that decimal point does play an important role here with respect to zeros. Okay. All right. Now that brings us to exact numbers. Up to this point, we've been talking about measurements. So remember, this measurements are something you have a ruler, you got a balance, something to measure volume. Those are measurements. There's a degree of uncertainty, but there are what are called exact numbers. There's no measurement there. They're exactly. So if you say I got 14 people, it's exactly 14 people. If I have a conversion factor, it says 3 feet per yard. There's exactly 3 feet per yard, not 3.4, 3 point whatever. It's exactly 3. 100 pennies and $1, 5 iPads, for example, whatever, or a 12-pack. Those are exact numbers. And being exact numbers, they would not play a role in determining your significant figures at the end. Okay. Now, remember on the periodic table, those atomic weights. Okay. Well, we never use the atomic weights to determine sig figs in our calculation. Keep this in mind. Why? Because those decimal numbers, the atomic weights, come from an average of whole numbers. Once we get into more detail of the atoms, you'll understand a little bit better. Okay, like for example, what is the average between 4 and 5? Nice whole numbers. What's the average? Remember how to get the average? Tally up the number, and in this case, divide by 2. Well, the average between 4 and 5, which are whole numbers and integers, is 4.5, right? Okay. Now, when you take the average of whole numbers, you have an infinite number of significant figures. Okay. And so you could say 4.5000000000 to whenever you got tired of saying 0. You have an infinite number of significant figures. And that is why the atomic weights are not utilized to determine sig figs in your calculations. Okay. Treat it as an exact number. That way, think of it as an exact number, even though it's a decimal number. But remember, they come from averages of whole numbers. Okay, so atomic weights are not used in calculating, determining sig figs. Exact numbers like the following are not used in determining sig figs. But measurements are. You measure something 7 inches, you weight it, 200 pounds or 10 ounces. Those are measurements in which you use tools to measure something, give it mass, volume, or length. Okay. Therefore, there's a degree of uncertainty. Therefore, they will play a role in determining the number of sig figs at the end of your calculation. All right, we're almost done. So anything measured is not exact. Okay. So the sig fig rules were not applied to exact numbers. So I tell you what, we're about halfway done. What I'm going to do, we got a couple minutes left here. Let me stop it here. And we're going to slide. We're on chapter 2, slide 16. All right, we're getting along pretty good. We'll finish this up on Tuesday and then jump into 3. And 3 is basically taking what we learned here in chapter 2 and doing calculations. And definitely be all done with the first 3 chapters, because the following week would be the first exam, which would encompass chapters 1 to 3. Okay. Don't forget, you got 2 labs per week. Oh, let me bring my little troublemaker here. She's always curious as to what's going on there. Anyway, if you have any questions, let me stop here. Hold on.